As we saw in Lewis dot diagrams for molecules, there are two different types of electron pairs that we can have. Shared pairs, which are our bonding pairs, and unshared pairs, which are our lone pairs. And each of these is going to have its own charge cloud, an area of space where the electrons are most likely to be found. And because they're all consisting of electrons, like charges are going to repel one another, so these charge clouds are going to have a repulsive effect on one another. And so they're going to try and orient themselves in such a way to minimize that repulsive force. And the more of them there are, then the more constrained those clouds and the arrangement of those clouds is going to be. So when we think about the effect of these charge cloud repulsions, how much repulsion there is and how many instances of repulsion there are is going to determine the arrangement of the orbitals, for one, the bonding pairs, if you will, and the arrangement of those bonding pairs or those shared pairs, those orbitals, helps us to determine the shape that the molecule is going to take on. And as you can see here, we have two different illustrations here. The one represents what we would conceive an unshared pair or a lone pair to look like, and it has that blunt pear shape, no pun intended. But if you think about it, if you have one electron, or electron pair, excuse me, on one atom, then those electrons are going to have a fairly, how do I say it, easy time to spread out and roam far and wide, because they only have one tether point, if you will, to that atom. Whereas with a shared pair or a bonding pair, you've got atoms on either side of that charge cloud that are going to have an attachment to those electrons. And so they're going to have a lot less freedom of movement, and therefore the charge cloud will be much more slender. And so if you think about it, one of these is larger than the other. And so depending on the combination of pairs you have adjacent to one another, it's going to impact the amount of repulsive force there is, and thus will lead to different shapes. So in order of repulsion, the greatest amount of repulsion would be between two charge clouds that are the largest shape. So if you have two unshared pairs about a central atom, that's going to create an enormous amount of repulsion, and any shared pairs that there might be, or we think about bond angles between atoms, is going to be much more constrained. Next in order would be one of each, one of the larger charge clouds and one of the more slender ones. And finally, if you have adjacent charge clouds that are both bonding pairs or shared pairs of electrons, that would create the least amount of repulsion. The differences that we see in the different molecular shapes results from this unequal space that is occupied by each of those electron pairs. And we also see instances where our central atoms, if they again are in the third row or lower of the periodic table, they have a certain exemption from the octet rule. It is possible in some instances for these central atoms to either exist with fewer than 8 electrons or more than 8 electrons. And so this is going to impact the number of electron clouds that there are, charge clouds around the central atom, and hence will also impact the molecular shape. When you have fewer than 4 electron clouds, sometimes you'll hear the term steric number used. Steric number is simply a fancy name for the number of electron groups there are around the central atom. So if you have fewer than 8 electrons around that central atom, say like 6 or even 4, then that shape will be two-dimensional in nature. It'll be a flat shape. But once you get to steric number of 4 electron groups or more around the central atom, now things become so constrained that the molecule actually becomes three-dimensional. And you'll see that in this next slide with a listing of shapes that you'll be expected to know. So what you see here is a list, not comprehensive, but the shapes that you will be expected to know and be tested on. You see a couple of different things here. The first two columns gives you a ratio of bonding groups of electrons or number of atoms that are bonded to the central atom. And the second column is the number of lone pairs on the central atom. And again, if you, when you look further over, then you see an estimated bond angle, the name of the molecular shape, and finally an illustration of what that shape might look like. Now, it's important to note when we talk about molecular shape, we're referring to the shape that is created by the atoms, not the electron clouds. On several of these, for instance, trigonal pyramidal, you see the yellow atom there. That actually isn't an atom. That's referring to the lone pair, the unshared pair, on, say, that would be ammonia. Okay, ammonia, NH3, would take on a trigonal pyramidal shape because it had the three atoms bonded to it, the hydrogens, and the one unshared pair that sat on the nitrogen central atom. So the best way, at least in my opinion, to learn these is to associate the molecular shape with the ratio of atoms bonded to the central atom to the number of unshared pairs. So for instance, a 2 to 0 ratio. You'd write out the Lewis dot diagram for your molecule, and if you note that it has a 2 to 0 ratio, 2 bonded atoms, 0 unshared pairs, then your molecular shape would be linear. Given that you have a molecular shape of linear, then you ask yourself, well, how far apart could those atoms get from one another? And the answer would be 180 degrees, and hence you have the bond angle 180 degrees. 3-0 ratio would give you trigonal planar. The planar part is indicating that the three outer atoms around the central atom are all coplanar to one another along with the central atom. So again, it's a flat molecule. And when you think about dividing up 360 among three atoms evenly, you get a 120 degree bond angle. If we go to a 4 to 0 ratio, you might think, well, okay, then we're going to split 360 degrees by 4, which will give you a bond angle of 90 degrees. But 90 degrees is really close, or really constrained for electron clouds. They really don't want to be that close. So what happens is those charged clouds actually repel each other and push and force the molecule out of plane. So it's no longer two-dimensional, it now becomes three-dimensional, and we get what we refer to as a tetrahedral shape. From the diagram, if you imagine each three-atom triangle of the outer atoms would represent the face of a tetrahedron. So you would actually have 4 faces to that geometric shape, and hence the name tetrahedral. You can see that when you look at those middle 3 shapes there, 4, 0, 3, 1, 2, 2, they all represent situations where we've got 4 electron groups, or a steric number of 4. So they all kind of belong to the same family, yet we see different names for the molecular shapes because, again, the shapes are determined by the atoms and their arrangement, not the electron groups. And so when we have an unshared pair substituted for a shared pair, remember they take up more space. So they're going to push on those shared pairs more and actually cause them to bend closer to one another. And so with trigonal pyramidal, we see a bond angle of 107. If we put 2 unshared pairs on there, we can strain that bond angle even more, all the way down to 104.5 with the bent shape. Some elements, central atoms, can again have more than 8 electrons, and so we see sometimes atoms or molecules that have a steric number up to 6. And so if we have a 6 to 0 ratio, here we do see a bond angle of 90 because there just is no other way to get 6 electron groups around the central atom other than 90 degrees. And so based on the atoms positioned to one another, this gives us an octahedral shape. If we substitute 2 unshared pairs for 2 of those bonded atoms, then if you think about it, remember that the unshared repulsion is the greatest. So those two charge clouds are going to want to be as far apart from each other as possible, which will be 180 degrees. So in looking at the diagram that you see there, all 5 of those atoms appear to be coplanar. If you would imagine one of those blunt pear-shaped electron clouds for the unshared pair above, directly above that pink atom and directly below, then they would be 180 degrees from each other, and they would be forcing those shared pairs, those slender shared pair charge clouds, to all be coplanar. They really don't want to be that way, but due to the presence of those unshared pair clouds, those large clouds, they really have no choice but to have a bond angle of 90 degrees. So again, to summarize, to determine the molecular shape, the first step you do is to draw the Lewis dot diagram, and then you assess the central atom and you determine how many electron groups does it have around it, how many atoms are bonded to the central atom, and how many unshared pairs. That ratio will tell you the molecular shape, and then once you know the molecular shape, you should be able to associate the bond angle with that molecular shape. And that part may take, each of those steps take some time to get used to those and practice with those, memorize the shape associated with the bond angle. But Lewis dot diagram, ratio of atoms bonded to the central atom and unshared pairs on the central atom only, okay? Determination of the molecular shape, and finally the bond angle.